To produce urine, the nephrons and the collecting ducts have three basic processes. The first step of urine production is glomerular filtration, where water and most of the solutes in the blood plasma are going to move across the glomerular capsules where they're filtered, or move into the glomerular capillaries where they're filtered, and then the filtrate is going to move into the glomerular capsule and then into the renal tubule. The second step is tubular reabsorption. So as that fluid moves through the renal tubules and through the collecting ducts, the tubule cells reabsorb about 99% of that filtrate and many of the solutes that are in there as well. Remember I said earlier, we filter out a whole lot more than we urinate out. 99% is reabsorbed. So the water and the solutes return to the blood as it flows through the peritubular capillaries, and also this straight network of blood vessels that is found primarily in the juxtamedullary nephrons with those long nephron tubes. So vasa recta, straight vascular network, is that network of blood vessels that works just like the peritubular capillaries. So those two together are going to reabsorb substances that leave the tubules and then return those substances to the bloodstream. All right, so remember, tubular reabsorption, things, water, solutes, leave the tubules and get back into the bloodstream. And then the third step of urine formation happens as that filtered fluid is going to flow through the renal tubules and the collecting ducts. The tubule and the duct cells secrete other stuff, waste products, drugs, excess ions, into the filtrate. So remember, reabsorption is to move substances from the tubes back into the bloodstream. Tubular secretion, the tubes secrete a waste substance that removes a substance from the blood. All right, so the solutes and the fluid that drain into the minor and the major calyces and then into the renal pelvis are going to be urine, and they're going to be excreted. So the rate of the excretion is going to be glomerular filtration plus secretion minus how much is reabsorbed. On average, about 150 in females to 180 liters in males are going to be filtered out every single day. So these containers that you see here in the bottom image represent approximately 150 to 180 liters. Now imagine that much filtrate being filtered out of the blood and into the or through the kidneys each day. Imagine if you had to excrete all of that each day. But we don't, because about 99% of that glomerular filtrate is going to return back to the bloodstream because of tubular reabsorption. So only about 1 to 2 liters, 1 to 2 Coke bottles, 2-liter Coke bottles, is going to be excreted each day. Glomerular filtration depends on three main types of pressure. One pressure helps or promotes filtration, and two of these pressures are going to oppose or work against filtration. So the glomerular blood hydrostatic pressure, that's just the pressure of the blood in the glomerular capillaries. And this is going to force water and solutes that are in the blood plasma through that filtration membrane. Then you have the capsular or inside the capsule hydrostatic pressure, and that is the pressure, the hydrostatic water pressure, that's pushed against the filtration membrane by the fluid that's already in the capsule. So you can think of it as a back pressure. So it's fluid in the capsule pushing back against the fluid trying to get out. So back pressure is opposing filtration. And then the third pressure is the blood osmotic pressure, sometimes called blood colloid osmotic pressure. And that's due to the proteins primarily, such as the albumin and fibrinogen, that are in the blood plasma. And of course, osmotic pressure is going to suck, so it opposes filtration as well. The amount of filtrate that's made in all of the renal corpuscles in both kidneys every minute is called the glomerular filtration rate. And of course that is an amount that has to be maintained in order for homeostasis. So if the GFR, glomerular filtration rate, is too high, substances that we need may pass so quickly through the renal tubules that some of them don't get absorbed and they end up getting excreted in the urine. If the glomerular filtration rate is too low, then almost all of the filtrate can be reabsorbed, and certain waste products get reabsorbed back into the blood as well, and we may not adequately excrete those. So there are some kidney diseases where the glomerular capillaries get damaged, and as a result of that, they become so leaky or permeable that the plasma proteins can enter the filtrate. That filtrate then is going to have a high osmotic pressure. That's going to draw water out of the blood, which means more fluid is filtered out. At the same time, the blood osmotic pressure decreases because the proteins are being lost into the filtrate. So as more fluid filters out of the blood capillaries and into tissues throughout the body, then returns back through reabsorption, blood volume decreases and the interstitial fluid volume increases. And this results, loss of plasma protein results in a condition that we call edema, which is an abnormally high volume of fluid building up in the interstitial spaces. In the average adult, the glomerular filtration averages about 125 millimeters per minute in males and about 105 millimeters per minute in females. And as I mentioned a while ago, body fluid homeostasis is going to require that the kidneys maintain a constant GFR. So the mechanisms that work to regulate the glomerular filtration rate operate in two main ways: by either adjusting blood flow into and out of the glomerulus or altering the glomerular capillary surface area that's available for filtration. So GFR increases when blood flow into the glomerular capillaries increases. Control of the diameter of the afferent and efferent arterioles can regulate the blood flow into and out of the glomerulus. Constriction of the afferent arteriole decreases the amount of blood moving into the glomerulus, and dilation of the afferent arteriole increases it. So there are three mechanisms that control glomerular filtration rate that we're going to look briefly at, and that's renal autoregulation, neural autoregulation, and hormonal regulation. The first type of regulation of GFR we want to look at are when the kidneys govern themselves, autoregulation, and they help to maintain constant blood flow, and of course that leads to a constant glomerular filtration rate. So there are two mechanisms that work together to maintain this constant GFR. The first is myogenic, and it occurs when stretching triggers contraction of the smooth muscle cells within the afferent arterioles. So once the walls, the smooth muscle in those afferent arterioles constrict or contract, then the lumen of the blood vessels gets smaller. That decreases the blood flow in, and as a result, glomerular filtration returns back to normal. On the other hand, when the arterial blood pressure drops, the smooth muscle cells are going to be less stimulated, less stretch, so they're going to relax. The afferent arterioles dilate, renal blood flow increases, and glomerular filtration increases. The second renal autoregulation is tubuloglomerular feedback, and it's named because there's a part of the renal tubules, remember, the macula densa, that are going to provide feedback to the glomerulus. So when GFR is higher than normal, the filtered fluid is going to move more rapidly through the renal tubules, and that results in the proximal convoluted tubule and the nephron loop not having as much time to resorb sodium and chloride and water. So the macula densa cells detect the increase in that sodium and chloride and water, and they inhibit the release of nitric oxide from cells in the JGA, the juxtaglomerular apparatus. Now, nitric oxide is a vasodilator. So the afferent arterioles constrict when nitric oxide declines. Remember, nitric oxide causes vasodilation. So with no nitric oxide, the afferent arterioles are going to be able to constrict rather than dilate, and this results in less blood flow into the glomerular capillaries, and GFR decreases. Second mechanism of regulation of GFR is neural, by the nervous system. So the kidneys have a great supply of sympathetic autonomic nervous fibers that are going to secrete epinephrine. Now remember, norepinephrine. And norepinephrine causes vasoconstriction. So under normal conditions, the vasoconstriction and vasodilation of the arterioles are mostly dilated, and the renal autoregulation of GFR pretty much takes care of everything. But when there's greater sympathetic activity and the sympathetic nervous system is stimulated more, such as when you're exercising or if you have a hemorrhage, then vasoconstriction of the arterioles is going to predominate rather than just normal vasoconstriction and vasodilation regulated by the renal regulation. So when the need is there, the sympathetic nervous system is stimulated more, vasoconstriction of those afferent arterioles happens. This results in the blood flow into the capillaries of the glomerulus being decreased, and that drops glomerular filtration rate. So the consequence of this is, 1, it causes a reduced urine output, which helps us to save blood volume, and 2, it also permits greater blood flow to other body tissues, because remember, the kidneys get 20 to 25% of cardiac output. The hormonal regulation is primarily due to angiotensin, angiotensin 2, which is a very powerful vasoconstrictor that narrows the afferent and efferent arterioles, and that reduces renal blood flow. Reduced blood flow, reduced GFR. The second is atrial natriuretic peptide. Now remember, this was something that you looked at with the nervous system. So stretching of the atria, for instance, when you have an increased blood volume and increased blood pressure, is going to stimulate the atria to release ANP. This causes relaxation of the glomerular cells and increases the capillary surface available for filtration. So glomerular filtration rate rises as the surface area increases, so that more fluid is filtered out. And on your next 3 slides, you have your summary tables of these mechanisms that regulate glomerular filtration. So your first slide here, you have your renal autoregulation with the stimulus and the mechanism of action and the effect of on glomerular filtration due to the myogenic mechanism and the tubuloglomerular feedback. All the things we just talked about. The next slide, you have your neural regulation, how it affects glomerular filtration, how that action occurs, and what the major stimulus for release is. And then you have your hormonal regulation, which are the 2 that we just talked about, your angiotensin, that powerful vasoconstrictor that's going to limit the amount of blood flow going into the glomerulus, decreasing your GFR, and your ANP, because of increased stimulation the stretch of the atria, releasing the ANP, and how that increases the surface area so that more filtrate comes out into the glomerulus.